In 2021, the Illinois General Assembly passed and the governor signed a law creating the Illinois Forensic Science Commission, which is helping guide the future of forensic science in Illinois. Members of the commission have decades of experience as scientists, lab directors, lawyers, doctors, academics, and community advocates who strive toward the common goal of making a positive difference on the criminal justice system in Illinois. The Commission, in collaboration with the Illinois State Police Forensic Sciences Command, the DuPage County Forensic Science Center, and the Northeastern Illinois Regional Crime Laboratory, developed this Fundamentals of Forensic Science video series as an educational resource for the public and forensic science stakeholders. Each video in the series will educate viewers on the science, technology, and methodologies underlying one of the core forensic science disciplines and serve as a building block for expanded forensic science education.
This presentation will provide an overview of the services and functions of a latent print section. A forensic scientist in a latent print section is responsible for a variety of tasks on a day-to-day basis. These include maintaining an accurate and secure chain of custody for all evidence, examining and processing evidence for the development of impressions, preserving any impressions developed, conducting analysis of the impressions in comparison to known standards, searching database repositories for candidates for comparison, keeping a written record of all work performed via case notes and reports, performing consultations, verifications, and technical reviews of other scientists' work, and testifying in court. You might be wondering, what is a latent print? We must first define a few other terms. If you look at the palm sides of your hands or the soles of your feet, you will notice raised ridges that form patterns. These raised ridges are separated by lower portions called furrows. You can think of this as the ridges being peaks and the furrows being valleys. This type of skin is only found on the palms of your hands and soles of your feet and is known as friction ridge skin. The function of friction ridge skin is to aid in your grip. Without this feature, the skin would be smooth and items would more easily slip out of your hands when grasped, or you would slip more easily while walking barefoot. Along the raised ridges there are pores. These pores exude sweat that coats the surface of the skin. When that sweat or other contaminants that you've touched coat the surface of friction ridge skin, and then you touch an object, you leave behind an impression of the patterns formed by the raised ridges of the friction ridge skin. These recorded impressions are termed fingerprints when they originate from the first joints of your fingers, palm prints when they originate from the palms of your hands, or footprints when they originate from the sole of the foot. When an impression of the friction ridge skin is left behind unintentionally, such as with everyday use of objects, it is known as a latent print. The term latent means not visible. Latent prints may not be readily seen by the unaided eye. One goal of the latent print section is to determine if latent prints are present. This may require physical or chemical processing of the item to develop the impressions and make them more easily visible. Once latent prints are recovered, they can be compared to known standards. When impressions of the friction ridge skin are deliberately or intentionally recorded, this creates a known standard. The person's identity is known and recorded. The standards are taken under controlled circumstances to obtain clear impressions with good contrast. Standards can be taken with the use of ink and paper or a digital scanning device, often known as live scan. One common type of evidence received is a latent print lift. A latent print lift is created by dusting an item with powder to make the latent print visible. Once a latent print is found, a piece of clear adhesive or tape is placed smoothly over the latent prints. The prints are then lifted from the item and placed on a backing that contrasts the color of the powder. This results in a latent print lift. Latent print lifts can be created at the scene of the crime and submitted to the laboratory in lieu of the item. This is typically restricted to items that are too large to collect and submit. When an item itself is submitted to the Forensic Science Laboratory for latent print processing, the scientist will first conduct a visual examination of the evidence.
This is done by looking closely at the item under different lighting sources and angles. Magnifiers may assist in this process. At any time during evidence processing, if an impression that could be later compared is seen, it is preserved. In this example, you can see a couple latent impressions are present, and this item would be photographed at the visual examination stage before proceeding on with evidence processing. During the visual examination, the scientist is also determining what type of evidence they have to process. There are two main categories of evidence: non-porous or porous. Non-porous items consist of materials that do not allow air or liquids to pass through or penetrate the surface. Therefore, any residue sits on the surface of the item. Due to this, the fingerprints on non-porous items are very fragile and could be wiped or washed away very easily. Examples of non-porous evidence commonly submitted to the laboratory include glass bottles and aluminum cans, knives, guns, cell phones, or gasoline containers. Porous items consist of materials that allow air or liquids to pass through or be absorbed into the surface of the item. Examples of porous evidence that are commonly submitted to the laboratory for analysis include checks and currency, threatening letters, or documents. Porous and non-porous evidence is processed differently. The processing paths deviate after visual examination.
During typical non-porous evidence processing, the next step would be to conduct cyanoacrylate fuming. Cyanoacrylate is the chemical name for a specific type of superglue. During this procedure, water is added to the chamber along with a few drops of superglue. The superglue is placed on a heat source, in this case a small hot plate. Test prints are added to the chamber to ensure the process works properly. And then the evidence is added to the chamber. The evidence is hung in a manner so that all sides can be coated with the superglue. Once the evidence is secured, the chamber is sealed and allowed to process. This has been sped up for demonstrative purposes. It takes approximately 10 minutes to process in a chamber of this size. Once the process is complete, the chamber is opened and the fumes are allowed to evacuate. Then the control or test prints are checked to ensure that the procedure has worked. This can be seen by a white coating or matrix that is formed over any residue on the item. This creates a hard shell over the fingerprint so that it is no longer fragile and is typically much more readily visible. Any impressions visible at this stage that are potentially of value for later comparison would be photographically preserved.
After the cyanoacrylate fuming adheres the print to the surface of the item so it can no longer be washed away, then dye stains can be applied to the item to further enhance ridge detail that may be present. Many labs do a two-part series of dye stain processing. One dye stain utilized is Ardrox, which is a yellow-colored dye stain that is washed over the piece of evidence in a fume hood. The dye stain is followed by a water rinse, and then the item is left to dry. Once dried, it is taken into a dark room and viewed under an ultraviolet light. It is imperative to wear UV protective safety goggles at this stage. When viewed, the impressions fluoresce or glow a blue-green color. Any impressions of potential value are photographed using a UV filter on the camera. After that, the second dye stain can be applied. Rhodamine is an orange-red colored dye stain that is applied in the same manner and followed by a methanol rinse. The item is again left to dry in the fume hood. And once dry, the evidence is taken back into the darkroom and this time is viewed under a laser light. Proper eye protection and a camera filter must be utilized for both safety and in order to properly visualize any impressions. Rhodamine stained impressions will fluoresce a yellow-green under the laser light. Any potentially valuable impressions must be photographically preserved for future comparison. This completes the routine processing steps for non-porous evidence. Porous evidence is processed along a separate processing path. Following the visual examination for a porous item, a common initial step is to process the item to target amino acids found in sweat from the hands. Techniques often employed for this purpose include 1,2-indane-dione and anhydrine. When using anhydrine, the item is dipped into a tray of the chemical solution. The scientist must ensure that the evidence is thoroughly coated, then the evidence is hung to dry. After the item dries, it is placed into a heat and humidity chamber. The heat and humidity speeds up the chemical reaction that is occurring. It is left in the humidity chamber to process. This can take anywhere from 20 minutes to 3 hours and is checked at regular intervals. Once the item is completely processed, any prints developed will be a purplish color and will be photographically preserved. Additional porous processing may be done to target oils and lipids present in fingerprint deposits. Some techniques that may be used are physical developer or oil red O. In physical developer processing, the evidence is first submerged in maleic acid pre-wash and left to rinse for approximately 10 to 20 minutes. The scientist watches over the evidence to determine the optimal wash time. Once the pre-wash is complete, the evidence is transferred to a solution that contains silver nitrate. In this solution, the silver will attract to the oil residues in fingerprints and deposit onto it. The silver nitrate solution is agitated across the evidence. It is then put into a water bath to rinse. This removes excess chemicals off of the item. Once removed from the water bath, the evidence is allowed to dry. A dark brown, black, or silver impression can be developed, which can be photographically preserved. Other items that may be submitted for fingerprint processing require more specialized techniques for that particular surface. A common example of specialized processing focuses on the sticky side of tape. This seemingly mundane material can hold crucial hidden clues. The adhesive acts like a fingerprint trap, readily capturing and protecting skin cells. Unlike prints on smooth surfaces, these are less prone to smudging. While developing prints on this surface can be challenging, two techniques are particularly effective. Gentian violet, which stains epithelial cells and other fingerprint components, and sticky side powder, a powder suspension that often produces excellent contrast even on this difficult surface. Once evidence processing is complete, a forensic scientist will begin to analyze, compare, and evaluate the friction ridge detail that they have preserved. This is known as the ACE-V methodology. The A stands for analysis. At analysis, the scientist is looking at all the detail present in the latent print to determine if it is of sufficient quantity and quality, or suitability, for comparison. If the print is deemed suitable, the scientist moves on to the C part of ACE-V, which is comparison. A known standard is introduced at this time, and the information in the latent impression is directly compared to the information present in the known standard. The E in ACE-V stands for evaluation. Throughout the comparison stage, the scientist is evaluating whether the two impressions came from the same source or different sources. This is the stage where a conclusion can be reached. And finally, V stands for verification. A verification is the independent application of the ACE process by another scientist to see if they reach the same conclusion. Let's take a closer look at how an analysis is conducted. During analysis, the scientist is looking at the detail present in the latent or unknown impression. Specifically, there are 3 levels of detail that can be observed in fingerprints. The first level detail is generally how the ridges flow and what pattern they make. It takes into account the overall size and shape of the impression. The second level of detail looks more specifically at the path the ridges take and the events that happen along the ridges that disrupt the flow. And the third level of detail looks very specifically at the ridge structure. This includes things like the width and shape of individual ridges, variation in the ridge edges, the size, shape, and location of the pores along the ridges, and incipient ridges. Let's break this down a little further and look at each level of detail more in depth.
When examining first level detail, the ridge flow is noted. This gives clues as to the source of the impression, in other words, whether it comes from a finger, joint, or palm. This can be determined by looking at the size and shape of the impression. When the impression comes from a finger, there are distinctive patterns present. The ridge flow of the impression in this image flows in and circles around. This is known as a whorl.
The 3 main pattern types are arches, loops, and whorls. An arch is where the friction ridges enter in from one side and make a rise, wave, or upthrust and flow out on the opposite side. A loop is when the friction ridges enter in from one side, curve up and around and back down, and flow out the same side in which it entered. And a whorl consists of 1 or more friction ridges that make or tend to make a complete circuit. Each of these main pattern types have subtypes that describe the flow more specifically. First level detail can be used to eliminate a candidate as being the source of the impression. For example, a latent impression that is a plain arch can be excluded as coming from the same source as a subject who has all whorls. However, first level detail cannot be utilized to identify an impression. In order to make an identification, one must look further.
Second level details look more specifically at the paths the ridges are taking and specific events happening along the ridges. 3 main event types that happen are bifurcations, ending ridges, and dots. A bifurcation is when a ridge splits into 2, like a fork in the road. An ending ridge is the term for an event where the ridge flows along and then abruptly stops. And a dot is a ridge that is no longer than it is wide, like the period at the end of a sentence. Second level detail, when looked at in totality, can be used as individualizing features to make an identification. Third level detail takes an even closer look, typically requiring magnification at the structure of the ridges. This can include incipient ridges, which are immature ridges that did not fully form. They are thinner and not fully formed ridges found between the thicker primary ridges. Another type of third level detail that might be present is a recording of the pores. When looking at pores, it is important to note not only the presence and location of the pores, but also the pore size and shape. The ridge thickness or width, the shape of individual ridges, and the variations in the ridge edges is another example of third level detail that can be utilized if present. Scars and creases may also be present and considered to be third level detail. There are no scars or creases in this example. Details seen at analysis are marked up on the image. The blue dots are a representative sample of the second level detail found in this impression. After analysis is complete, the analyst will move on to comparison. During comparison, a known standard is introduced. Comparison is conducted by examining the images side by side and looking for those details found in the latent during analysis to determine if they are or are not present in the known standard.
The comparison culminates in the evaluation process. A range of conclusions may be reached in latent print examination. While specific practices and terminology can vary across different organizations, commonly recognized conclusions often include an identification or source identification, a no identification or source exclusion, or an inconclusive determination. The determination of conclusion is based on a thorough assessment of all available information and the application of established forensic principles. If the result of the comparison to the known standard results in a no identification conclusion and the impression meets set standards, it can be searched in the automated biometric identification system. This is the repository of known standards within the state of Illinois. This database contains known fingerprint and palm print standards of a variety of individuals to include criminals as well as civilians, such as police officers, teachers, taxi drivers, and more. There are currently more than 6 million subject standards in the state database. Even though the system is termed automated, it does not identify impressions. It provides a list of the closest matches the system finds, and then a scientist manually compares the latent impression to those candidates.
There are two principles that form the foundation of utilizing fingerprints as a means of identification. These are the idea that fingerprints are formed before birth and remain unchanged throughout a person's lifetime. This means that your fingerprints are substantially the same each time they are examined. Even if you damage your fingers and leave scars that do alter your prints, those scars become permanent from that time forward and can be also used in comparisons. In addition, due to the nature of the formation of ridges, fingerprints are different from person to person and even finger to finger on the same individual. Even identical twins have fingerprints that are distinguishable from each other.
In this presentation, you have learned what a latent print is, how they are developed, how comparisons are conducted to known standards, what conclusions can be reached as a result of that comparison, and why fingerprints can be used as a means of identification.